let me try to summarize the pseudocode given in the book to report the intersections correctly and handle the degeneracies at the same time. Okay, the general algorithm, the main function is very simple. All we need to do is, first we create an event queue consisting of the endpoints of the line segments. We name these endpoints upper endpoint and lower endpoint because we are sweeping from top to bottom. And you may think about degenerate cases like, what if we have a horizontal line? What is its upper endpoint and lower endpoint? Okay, if we have a line segment like this, how do you define its lower and upper endpoint? What we do is, in such cases, remember we ordered these endpoints lexicographically, meaning that we assume we are going to reach this, if they're at the same height, the event points are going to be processed from left to right order. So imagine the sweep line slightly tilted to the right. So when you're sweeping, you are going to reach this one first. So since we do this lexicographic ordering, such degeneracies are already handled. So if there are multiple event points on the same event point, on the same sweep line, we process them from left to right. We need to, while proving the correctness of this algorithm, handling event points from left to right. For example, one question would be, remember, we need to consider when we were ordering the lines with respect to how they cross the sweep line, such lines, for example, they cross the sweep line, they intersect the sweep line at infinitely many points. Okay, what is this going to be its unique x coordinate that I'm going to use to sort this? If you consider it like this, for example, at this point, you may think, this is the first event point you come with this line. At this point, you may say that I intersect the event point at this first x1 and x2, and if nothing changes in between, I can sort this line. I can give an order to this line, imagining that it intersects my sweep line at this event point, which is actually going to be similar to what the solution we have here. So if you think about this, we can handle horizontal lines with the help of this left to right ordering of the event points on the same sweep line. Now, the difficult cases are cases like these. Okay, difficult cases are cases in which multiple line segments have the same intersection point. And there was a very nice question during the break. For example, this S5 and S3. Consider S5 and S3. Okay, they intersect at this point, but they were never neighbors until they intersect at this point. So will we be able to correctly report S5 and S3 as intersecting line segments? Because this is the place they become neighbors. I mean, due to all these other line segments that were in between, they were never neighbors, so we never check S3 and S5 for intersection. So will we be able to correctly report them as intersecting points? So these degeneracies are more difficult to handle, but we are going to see the idea of looking at the three different sets of line segments is going to solve this problem, and the ordering of the tree. So the main function is like this. So we initialize an empty event queue, and we insert all the endpoints, lower and upper endpoints, into this event queue, prioritized by their y coordinate. So the higher y coordinate event points will appear first in this event queue. So it's going to simulate a horizontal sweep line going downwards. Now, and the main function just is this: get the next event point until the event queue is empty, get the next event point and handle it. Okay, the actual code is the handle event point function, which is going to find intersections and which is going to handle this ordering of the status tree. So the handle event point is our main function. If you have a copy of the book, you can check. The handle event point is the actual function that does all these checks. Okay, so until the event queue is empty, we handle event points one by one based on their priority, based on their y coordinates. So the handle event point is the complex one, and here's what we do. We have two sets of line segments, and these line segments can be found. This LP is the set of line segments which have P as their lower endpoint. For example, in this example here, S4, and let me erase these other things. Here, S5 was also ending here, right? So S4, let me check the, yeah. S4 and S5 are going to be in this list, in this example. S4 and S5, the line segments whose lower endpoint is P. And we have these segments S4 and S5, we can immediately access these segments because at this event point, these segments are stored with the event point. When we first so event point is, you can think of it as a class, as an object, which has both its y coordinate, x coordinate, and a list of associated line segments with it. So at this point, since when we insert this P as a lower endpoint of these segments, we also store the segments with the event point. Okay, the event point has access to the segments related with it. And UP is the segments which have P as their upper endpoint, and here UP is S2. And CP is the set of line segments which contain this event point P in their interior, which is the difficult case to find, because here to find CP, either S1 and S3, okay, 4, 5, 6, 7, okay. So finding S1 and S3 may be trickier, okay, because when we inserted this P, S1 and S3 may never become neighbors before. For example, I mean, if this P was detected as an intersection point earlier, S1 and S3 both may be associated with P at that point. But imagine we have S5 going like this, which also has P as its interior point. So imagine S5 is not here, but we want it to be here. Now at this event point P, we have never actually encountered S5. Maybe before this point, S4 and S5 may be tested, and this intersection may be reported between S4 and S5. So we may know in previous event points, S5 may not be neighbors with S4 and S3, but it was neighbors with S4. Okay, it will be neighbors with some other segment which has its intersection, which is going to detect this intersection between these two. So S5 can be detected as earlier as an intersection point. But what the book suggests is that we don't, even if we don't store these line segments which has P in their interiors, we can find these because on the tree, because these are going to be, I mean, if we do a search on the tree using point P, Okay, if we have a balanced binary search tree, and we can search this tree with a line segment, but we can also construct an imaginary line segment with both endpoints x1 with point P here. If we do a search on this tree with event point P, the book says that we are going to find these line segments because they are going to be, all of them are going to be neighbors in the tree. So if we look at this event point and we look at our tree, all of them are going to be neighbors. For example, S7, between S7 and S8 on our tree, just before coming to here, between S7 and S8, we should have all the segments that are associated with P as a neighbor on the leaves of this tree. So this is how we can find CP. Now let's get back to the original figure from the book, in which S5 is here. Now, here's what we do. After we determine, okay, we find LP, UP. Okay, it also says for horizontal segments, the upper point is by definition the left end point. So it says find all segments in this tree that contain P. These segments are adjacent in the balanced binary tree, and we have the LP and CP, which are defined, the segments that contains P in their interior and as their lower end point. Now, the algorithm is like this. If the union of all these sets, okay, if we take the union of all these sets, if it contains more than one segment, it means that all pairs of elements in this union should be reported as intersecting segments. Okay, I mean if we have some segment which has its lower end point as P and another segment as its upper end point, and if we take the union, so it's just say if LP union UP union CP, if this union contains more than one segment, what we do is we report this P as an intersection point together with together with these. We say that S1, S3, S2, S4, S5 intersect at point P. Okay, so this is the first case. Now we report all of them as intersection. Now what we need to do is, at this point, the intersections related with P are reported correctly. At this point we handled event point P, but now we need to rearrange the tree. Now we need to reorganize the tree based on how the study structure is going to look like after P, and also just after that, if there is some possible potential intersection that we can observe after event point P, we need to detect them and insert them as events into the event queue. So the two things left are, after we find these sets and saying, okay, this union, or the segments in this union are intersecting at point P, as an intersection point, we are done with P. But now the next thing we need to do, as I repeat, we need to find possible intersections below P, and we need to delete segments from our study structure, and we need to insert segments into our study structure, and we may need to reorder them based on how this order of line segment is going to appear below this event point P. And this is how it is done. First, we delete the segments LP and CP, so these segments are deleted from the tree. And we insert these two, so these are deleted, these two are inserted into the tree. And the order of the segments in T should correspond to the order in which they are intersected by a sweep line just below this L. If there is a horizontal segment, it comes last among all segments containing this sweep line L. Okay, so this is if we are going to order, so this statement shows that how you are going to order a horizontal line segment in this studies tree. If there's a horizontal line segment, it should come last in all segments that contain P. If you are going to order it, it should be, for example, if there's a, okay, being a horizontal segment means this, because it's its beginning endpoint, or it may be something like this. If we didn't delete it, if it wasn't like this, if its endpoint was not this, there must be something here, and it is going to come last in the order based on the sweep line just below L. Why is it going to come last? If you just think about this order, so this ray, I mean such kind of a rotational sweep gives us the order of line segments just below sweep line, and this one, as you can see, if there's a horizontal line segment in this order, this horizontal segment comes last in the order how they intersect the sweep line. Okay, so this is also this statement also handles the order of horizontal line segments on the study structure. So deleting the CP set first and then reinserting it is going to change, is going to reverse their order, but we don't need to think about reversal right now. We just know if we have a good comparator function, we are just going to, we can say that we are going to order them correctly just based on a sweep line just below L. Now, here is the important part. We updated our study structure. Now our study structure is correct, but now what are the potential new intersections? We need to now here test only the pairs of line segments which can potentially intersect. Okay, so here this is what we do. If first of all, what can happen is that this UP and CP sets may be empty. Okay? If the union of these two sets, UP and CP, remember these are the ones that are going to be inserted into the tree, and these are the ones that which are already in the tree and which are not going to be deleted in the tree. If these two sets if there are no such line segments, means that we were only having line segments in this event point P which has their lower endpoints, meaning that we're just deleting things from the tree. Now, are we done at this point? No, because deleting these line segments, deleting LP from the tree, what it made was, it made some, like S7 and S8 became neighbors after these segments whose lower endpoints are here are deleted from the tree. So even these two sets are empty sets, even their union is empty, what we need to do is we need to find the two segments SL and let's name that the left segment and right segment, immediately the neighbors of this event point P in the study structure. So our study structure should be able to support queries like this. Given that we need to be able to query a point P in the study structure, and that P does not, may not correspond to a line segment actually, but we need to be able to find the left and right neighbors, immediate left and immediate right neighbors of some point P on the sweep line. Okay, we need to access this S7 and S8 in log n time in our balanced binary search tree. All these things make the implementation of this algorithm difficult, but it is possible. I mean, you may support such queries in your balanced binary search tree. Given a point here, find me, and existing libraries like hash sets and other tree sets in C++, they allow range queries. Okay, Range queries meaning that give me all the objects in this tree which are between this and this. So you can say you can indicate ranges and it will give you range. So it can also, by providing a certain range around P, you can find this left and right neighbors, and these are the ones that should be tested. These are the ones that can potentially intersect, and this is what you do if you P and CP, their union is empty. You need to test for intersection between S7 and S8. And if they are not empty, what you do is you look at the union of this set, and you pick the leftmost point, leftmost segment in this set, and rightmost segment in this set. If it's not empty, what it becomes is that, if it's not empty like this, potential intersections is between the leftmost segment in this set, S3 and S7, and S1 and S8, the rightmost segment and this right neighbor. So we need to find these two leftmost segments and left neighbor, and we need to check potential intersection, and we need to do the same thing for the rightmost segment. So this concludes the algorithm. Okay, so all we need to do is, after we delete these numbers and report this intersection, we update our studies tree and we check for potential new intersections between these line segments. And when we are doing find intersection, we need to be careful. This was also your homework. The same intersection event may be detected before. And during this potential intersection check, you may be detecting the same event point again. So you need to make sure you don't reinsert it to the queue. You don't double it. But what you do is, if the same intersection point is now involves other segments, then you can record these other segments in this already existing event point. Okay, so this concludes our discussion about line segment intersection. Since we don't have much time for map overlay problem, I'm going to assume, since if I answered all your questions, you should now be convinced about the correctness of the algorithm. So I'm not going to talk about the correctness of the algorithm again, because you asked really good questions, to question the correctness of this algorithm. The book actually proves this, but even does not answer all of your questions when it's proving. So the algorithm reports all intersections. It doesn't miss any intersection. And also it runs in n log n plus I log n time, where I is the number of intersections. So the first n log n is to sort the endpoints, and I log n is the number of intersection. I is the number of intersections. So if I is potentially if there are n square intersections, the second part is going to be n square log n. But if you have smaller number of intersections, n log n is going to be the dominating term in this complexity. All right, any questions about line segment intersection? Any points not clear? Are you convinced that the algorithm is correct? Maybe still questions in your mind. But everybody should agree. This is a difficult algorithm to implement, right? It's not going to be 100 lines of code. There are lots of smaller details that you need to handle. So I've been teaching this line segment intersection, the sweep line solution, to the informatic Olympians for the last 3 years, and they haven't been able to implement it yet. So even their instructors, and they have research assistants that even they say, okay, we haven't been able to implement line segment intersection yet. And also they know all the sites like Topcoder and all, the the coding, the problem sites, and if there's an existing implementation, they would know, okay? So they also would not be able to find anybody on the internet who was able to implement this. So it's a difficult to implement, but actually I tried to implement it and in Java, and I finished implementation, but it doesn't work 100%. I have a bug in my program, and maybe I can solve that bug after. I didn't use, for example, the idea to test the order of two line segments based on this midpoint. This just came to me today. I mean, I was just using, my comparator was based on a single pivot point. So how do you compare two line segments given a pivot point? Maybe that part was incorrect, I don't know, but it doesn't run fully correct. My implementation is not correct yet. But it was like 400, 500 lines of code, so it's a complex code. Yeah, that's all. We don't handle such situations. We ignore. Maybe you can detect such cases. So the question is really good. Another degeneracy that could happen is that two line segments partially overlapping. So they intersect at infinitely many points. Such cases may happen if you have at least 3 points that are collinear. And usually when you are given input, I mean, if you are faced with a question, some kind of a coding competition, usually the inputs may guarantee that there are no 3 points which are collinear. If you guarantee that, I mean, that's a big restriction in real life. I mean, you are going to have, if you are just going to generate random points, many of them, many triples are going to be collinear. So you cannot guarantee that. But such partial overlaps can be detected maybe in the pre-processing step, and they can be removed from your list if such cases happen. But this algorithm does not handle partially overlapping line segments. Mm-hmm. Okay, I got the same comment from the coders in our Olympiad team all the time. So what the question is, using the O(n)² solution may be faster, okay? Which is not faster actually. In real life, implementing it may be faster, okay? It may be only 50, I mean, even 30 lines of code, you may implement the brute force solution, which is going to check the existence of intersection between every pair of line segments. This is what you mean by brute force, right? But this n², if you try to run it really on 10 million line segments, it's not going to finish in a reasonable amount of time. And if you're, for example, you're limited, for example, your algorithm should finish in 10 seconds. You need to give some answer in 10 seconds. The algorithm described in the book, although it is very difficult to implement, although it's going to take, I mean, in terms of implementation time, the book in the algorithm is like an exponential implementation time algorithm. It's going to take a lot of time, but if you can implement it, it's going to, any correctly implemented algorithm is going to run in seconds. So the difference between n log n and n² is huge when asymptotically. And n log n is much closer to the linear running time. So the difference is good. It's not n², the brute force is never going to be able to compute with this. Yeah, n² log n and n² are not, yeah. I mean, if you're thinking about additional complexity we have, if there are many intersections, for example, if the number of intersections is n², of course, n² log n is going to be greater than n², but as you mentioned, n² log n is closer to n². Then the difference between n² and n log n is almost comparing n² with n. Okay, so it's almost linear. So log n is a very fast decrease, a very slow growing function. So therefore, if implementing this algorithm is going to gain you a lot. And For example, if you're working in a GIS company, which is going to develop a geographic information systems tool, you need to implement this algorithm if you are going to look for bridges. If you have such a query, find bridges in this road, river intersections, you need to implement this algorithm to be able to compete in the market. Yes?
Biraz öncekinde bir transition noktasının altında hepsi aynıdır. Uzaklaşmaya başladıkça bundan şey yapacaktır. Bu yüzden tightly below of the intersection point alacağız dedik. Event point'te arasında olan herhangi bir event point'le bu intersection point'in arasında olan bir noktayı alabiliriz.
Bir çizgi.
O event point intersections'da bir sonraki, şimdi bizim buradaki örneğimizde intersection yok. Bir sonraki event point intersection olabilir ama yani S8'deki kişi olabilirsin o.
No, it doesn't matter. If any type of event points. Oh, okay. Okay, I see what you mean. Okay, so what you mean is when we are ordering if, for example, we take the middle point, but what if there appears another event point just before the middle point? What will happen? So, I mean, this shows that my middle point solution is not correct. This is a good example. So, we need to, but the book's solution is just tiny bit amount of sweep line is going to work in this case. So, how we are going to implement this? I mean, just if you're in a discrete, I mean, if you're in an integer space, you can think about just looking at one unit before. But again, there can be an event point at that point. So,
Some preprocessing.
Yeah, maybe. Yes. Oh, okay. Okay, so that's a good idea. Instead of comparing them based on how they intersect, we can maybe, I mean, this rotating idea can be used. I mean, it's just like, I mean, this rotational sweep. During this rotational sweep, maybe you can look at the slopes of these line segments to be able to sort them based on how they will appear just below the sweep line. Yeah, that's a good idea. For horizontal, yeah, I mean, there will be infinite slope lines, but we are going to handle them maybe in two cases. The left part and right part can be sorted separately and combined at the end. I think it may work. But as I said, I mean, the book even does not, I mean, this is a simple small detail. But if you're going to implement this, these small details are really troublesome. Sometimes they can be. I mean, the question is, you need to be able to have a correct order of these line segments just below this event point. What I did was actually my solution was not even using my original solution that I implemented, is just by using this point P as this pivot point, we may be able to compare two lines based on a pivot point. It's like this. Imagine, and you knowing which way you are going, from upper to lower. If you know how you sweep the plane from upper to lower, all this, I mean, you don't need to think about this complex case where there are many lines. We don't need sorting. The sorting is done by the binary search tree itself. Okay? All we need is a function that compares two line segments based on a given point. Okay? Given this point, just tell me whether L1 is going to be smaller than L2 or L2 is going to be smaller than L1 based with respect to this event point P. So I think this you should be able to write a function for this. It doesn't seem like a very difficult problem. For some lines, for example, there is a total order among certain lines. For example, if your lines are like this, okay, actually we are doing X, we are storing them, we are ordering them with respect to their X coordinate. Now the question I mean, the function we are going to write is like some kind of a checking is left. For example, is L1 left of L2? Okay, we are going to write a function like this, is L1 left of L2? But for lines like this, if both endpoints are to the left, these are easy cases, it returns true. If both endpoints are to the right, it returns false. But tricky cases become when neither endpoints are, for example, for cases like this. For example, if you look at this endpoint, it's not, but still, you can, if you look at this, you can still, if you look at these things, you can still say that there's a total order between these two line segments. This upper one, this one, L1, L2, you can say L1 is to the left of L2, irrespective of any pivot point. All you need to do is you extend, okay? If you extend these things, you see that L2 completely lies to the right of this line from beginning point to end point, okay? So you cannot say it for L2. I mean, you can, for example, for these two lines, you can, L1 is always going to be to the left of L1, whatever sweep line you choose, okay? Wherever the sweep line is, if you have such a case, L1 is always going to be left of L2. And the difficulties arise when these two intersect. In all these cases, when they do not intersect, we can uniquely say which one is to the left of the other. If there is intersection, this is undefined, because above the intersection and below the intersection, the left of the order changes. And all we need to do is maybe treat them, since we know this intersection point, this pivot point, I mean, this intersection point is going to be the pivot point between these two things. And if you're asking the order above some point, this pivot point, you are going to look at these two line segments. You can chop these line segments into two smaller line segments and ask which one is left of the other by looking at these two line segments. And if the point you're asking, the comparison function you are doing is below this point, P, then you can, all you need to do is check whether these two smaller segments, which one is to the left of these smaller segments, okay? And this can be done. We don't need to, we don't need to consider an imaginary line segment here. Below this point P, this is always going to be any sweep line you choose, this one is always going to be to the left of this one. Okay, so all you need to do is consider these things to make a comparator, to compare two line segments. This is all we need. We don't need to sort them. The balanced binary search tree, its goal is to sort it, okay? The binary search tree sorts them if you just with the insert operation, if all you need to do is provide a comparison between two line segments. If you have a comparison function between two line segments, as you insert them into the tree, they are going to be compared to the segments at the intermediate nodes in this tree also contain a copy of the segments to guide the search, but all the segments also are stored in the leaves. And during this insertion, it's going to be inserted into its correct order. So if you insert all of them one by one into this tree, at the end you have yourself your sorted order of segments on the tree. Okay, good. All good questions. Yes? So there are different implementations of binary search trees. Especially balanced binary. If you're going to guarantee the balanced property of the binary search tree, usually during an insertion, maybe to the leftmost, always you may be inserting to the, if for example, if you're given an already sorted list of segments, as you're inserting, you're always going to insert them to the right, to the right, to the right, and you're going to violate the balance property. So different techniques ensure the balance property of the tree in a different way. They have some rotations, and if you remember, red-black AVL trees are different, red-black trees are different. So a particular implementation at the end may end up with a different tree than yours. But all of them, they need to ensure that the height of the tree and leaf node any leaf node cannot have a height smaller than h minus 1 in this tree. If height of the tree is h, at least all the leaf nodes should have a height h or h minus 1. Okay, so as long as they guarantee it, you may have a different, and as long as they are sorted on the tree, you can have different structures in the tree. Different branches may occur in the tree. Okay, let's have a break for 10 minutes.